Alright, cool. Well, it's about that time. Get started. Hopefully, folks will come on in here. Last time we spoke about the kinematic equations, so that was real nice. Time, velocity, speed. Anything you want to say before we get started? Anything that came to mind this week? Anywhere you saw physics applied in your life?
Not anything I like. Kind of caught me, but it's all around us anyway. So
Yeah. Still looking at those videos.
Yeah.
Yeah. Astronomy is always fascinating.
Oh, man. It gets me every time.
Yeah. It's crazy how huge these objects are, and the forces at play, the speeds, the movement. Like it is awe-inspiring. Awesome. So we talked about the motion equations, talked about time, velocity, speed, acceleration, the motion equations, constant acceleration, and then problem solving. Hey, great day, welcome in. So also talked about the problem solving basics. We talked a little bit about that as well, which we've been setting up those steps all throughout the time, just having our free body diagram and knowns and unknowns, and then the equations, substituting in what we have with the units. Ask, is this answer reasonable? If it is unreasonable, ask what could make it look more reasonable. Alright. So the next part that I didn't go to as much, unreasonable results. Solve the problem using strategies as outlined and in the format followed in the worked examples in the text. Check to see if the answer is reasonable. If the answer is unreasonable, look for what specifically could cause the identified difficulty. So we were able to talk about that. So now we're on falling objects, which mainly has to do with gravity. Describing the effects of gravity on objects in motion of objects in free fall, and then calculating the position and velocity of objects in free fall. So we know a lot about gravity. Most remarkable and unexpected fact about falling objects is that if air resistance and friction are negligible, then in a given location, all objects fall toward the center of the Earth with the same constant acceleration, independent of their mass. This experimentally determined fact is unexpected because we are so accustomed to the effects of air resistance and friction that we expect light objects to fall slower than heavy ones. So in air, having a friction environment, of course, we're experiencing certain principles where airflow is flowing through this feather and everything, but in a vacuum, it doesn't matter, which is pretty crazy. It's pretty wild. So, and then they both fall at 9.8 meters per second squared. So that's the acceleration due to gravity, gravitational acceleration. So that's the 9.8 meters per second squared. For the ideal situations of these first chapters, an object.
That's the equation?
No, that's just That's just saying gravity. That's just saying what gravity is.
Oh, okay.
Yeah. An object falling without air resistance or friction is defined to be in free fall. Did y'all go to the free fall ride in Six Flags when they had it? That's every time I hear free fall, I always think of the ride at Six Flags. It was a ride where you're sitting down in this slope cart, whatever, but they go up and then you move forward just a little bit and then they just drop you down. So you just get cranked up and then you move forward a little bit and they'll drop you down so you're going vertically, going down, and then the bottom just opens up and then you're going and then you like go down on your back. And yeah, so every time I hear free fall, I always think of that ride. I always know, oh, free fall, we're just going straight down. So yeah, 9.8 meters per second squared. So that's that. One-dimensional motion involving gravity. So now we're about to get into some of the equations where gravity is very important. So much like here, start considering straight up and down motion with no air resistance or friction. These assumptions mean that the velocity, if there is any, is vertical. If the object is dropped, we know the initial velocity is 0. Once the object has left contact with whatever held or threw it, the object is in free fall. Under these circumstances, the motion is one-dimensional and has constant acceleration of magnitude g. We will also represent vertical displacement with the symbol y and use x for horizontal displacement. So here's the kinematic equations for objects in free fall, where acceleration is negative g, where it's going down, where we want to say going down. So velocity equals the initial velocity minus the gravitational acceleration times t.
So that's at 9.80 times
meters per second squared, yeah. Yep. So if you see, and then you'll see y, initial y plus initial velocity times t minus 1/2 gt squared, v naught squared minus 2g, y minus y initial. So if you'll see, these equations are very similar to these equations.
The velocity equations.
Yeah, the kinematic equations. Here we are. So we have just see, these are the v naught plus at, x, so that's horizontal. We were talking about cars, talking about walking, so that was x, more so in x position. V squared velocity, right? So
Now we're going into the y position.
right. So now we're looking at y, and then we're adding in the gravity along with it. Yep.
So we're doing y and x.
Yeah, so if it's just something like this, falling object, a rock thrown upwards, it's only going to be up and down. So it's a little bit easier until we start getting into vectors and components, the two-dimensional kinematics, where it's x and y. So right now it's one-dimensional, x or y. So it kind of sets us up in flow to say, oh, okay, here's x, and then here's just y, and then here's something where it's x and y. So our lab will help us enforce that two-dimensional.
So once we start drawing the vectors, that's when it adds the x and the y components.
Yeah.
Gotcha.
Yeah, typically, yeah. Yeah, you can do vectors with this too, but
It's really just in.
it's gonna be one, right? It's gonna turn into one because the angle is the same. So,
That makes sense.
yeah, so we're about to look at something like this. Throwing a rock up, like down, throwing a rock straight down. ing from a falling object. Cool, so these would be good to go ahead and go over. One-dimensional motion involving gravity. So we just talked about those. All right, example 2.14. Calculating position and velocity of a falling object where a rock is thrown upwards. A person standing on the edge of a high cliff throws a rock straight up with an initial velocity of 13 meters per second. The rock misses the edge of the cliff as it falls back to earth. Calculate the position and velocity of the rock 1, 2, and 3 seconds after it is thrown, neglecting the effects of air resistance. So draw a sketch. So and then where we have initial velocity. So if we're given body diagram. And then 2. That's unknowns. 3. Let's look at our equation. Units. 4. Solve. Reasonable. Alright. So I just put that up there just in case we go through any questions.
Okay, so first we see that your initial is 13.
Close that. Right.
And A is the acceleration. Is that?
Mm-hmm. 9.8 meters per second squared.
So that means the gravity,
Mm-hmm. Yeah, it's the same thing.
like the gravity constant of
Yeah. So now we're looking at knowns, unknowns. So I know I'm given now I'm given V naught. I pretty much have it there. Hey, so now I'm gonna go to the equations. Well, I need to ask, what's my unknown? Question mark. Calculate the position and velocity of the rock. So position and velocity of the rock. So X final and B final. 1, 2, and 3 seconds later. Time equals 1, 2 seconds, 3 seconds. So I would say that would look something like that. So I have some knowns and unknowns. If I look at my equations, looking for something to get me, so we have velocity. We can put in our initial velocity because we have to get our final velocity. So that's gonna help out. And then I said X, but we're only dealing with the Y direction here. So it's not going to be an X final, or my final position, because there's no way for it to go X. It's only a Y.
But how do you go about picking the equation?
Well, we're going to look at what we have already and what we're looking for. So I see that there's a V final, and then a V initial, so that would help out. And then I don't have, see, like, take for instance the third equation, I don't have my final Y, and I also don't have my final velocity. So it's going to be kind of difficult to have the final velocity and the Y put together. But if I find the velocity first, then I could plug it into that third equation, something like that.
Oh.
You know, like I don't have enough information. If I have two unknown variables, it's going to be a lot harder for me to find the final answer.
So, I know you're jumping ahead, but are we using all three of these formulas at some point? Like the first one for velocity, the second one for position, and then we get those answers and plug it into the third one?
No, I think for this one, it'll just be 2.
The second one?
Yeah, I know for sure. I think it's just gonna be 2, because might not. Yeah, I think it's just gonna be 2. Let's take a stab at it. Alright. So the first equation, B equals B naught minus G and then T. So if I have B, should have initial velocity, gravity. And then time, I still need to have my time. So let's see what they say.
1 second.
Yeah, so that's gonna be the.
Oh, we go through all of them?
But I need T.
Oh, okay.
Oh, okay. Yeah, well, I need my. See, that's why the first equation is difficult, because I have. Let's see here. See what happens when we do T is 1 second. Let's see what happens if it's the same as going step by step. Or we need that. Alright, so 13. Let's see what happens. 13. So this will be 1, a negative 9.8, but it's minus 2. So it's really plus. I get 22.8 meters per second. So that's what I get when I get into the first one. So and then that's the first equation. And the second equation. Y and that. Yeah, see, it's asking for. Yeah, it was asking for final velocity. So I'm surprised that they didn't start right here for the first equation. Because it's asking for our final velocity. But let's keep on going. Because they just skipped, looks like they skipped that for the first step. But let's keep on going. So this will be for 1 second. 2 seconds. 3 seconds. So 9.8 times 2 is 19.6. This time it will be 13 plus 19.6. 13.6 and we have 3 seconds. Uh, 9.8 times 3, 29.4, and 13 plus 9.4. Alright, 42.4. So now that I have my velocity, my final velocity, remember just the V. So the final velocity. So I could plug that into the. Alright, so here's the second equation. So Y equals my initial Y, which should be 0. Plus V naught T initial velocity, 13 meters per second, times t 1 second, minus 1 half, negative 9.8 t 1 second, squared. So this is what I get for the first one. Oh, that's not right. Meters per seconds. That cancels out. And then x squared, so that cancels out. 13 plus 4.9, 17. Cool, let's see. I think it's something else. Plug in the known values. So we did that, the 13, the 1. Why is it plus 1 half? Here it's minus 1 half. Oh, because it's going in the opposite direction. Yeah. So the minus. Going down, probably because we went up. Yeah, maybe because we went up first. Yeah, I guess because he threw the ball up. So maybe when we get to the next part, that'll be plus, and that'll be minus. That means when we get to the next part, yeah, so I get the same answer now. So I'm sure when we get to the next throwing the rock down, looks like it'll be a negative. So yeah, that's the part that I'm mad that they did that one on. So we use plus and minus signs to indicate direction, with up being positive and down being negative. Since up is positive and the rock is thrown upward, the initial velocity must be positive too. So that's something to think about. So, and then we already did t for 1. So and then it would be the time being 2 seconds. So then we'll just put it in to velocity. Solution for velocity. Identify the knowns. We know that y naught, v naught, a, and t. We also know from the solution above y1 equals 8.10 meters. Identify the best equation to use. The most straightforward is v equals v naught minus gt. So we did do that from v v naught plus at, where a, blah, blah, blah. Plug in the knowns and solve. So my initial